Good day, ma'am. In this presentation, we will be talking about chemistry of water treatment. First, why do we do water treatment? First reason is to minimize the amount of potentially harmful organisms in the water and to make the water aesthetically good. Parts of water treatment: coagulation, softening, mixing and flocculation, sedimentation, filtration, disinfection, adsorption, and membrane. The first part is coagulation. The main object is to turn smaller particles of color, turbidity, and bacteria into larger flux, either as precipitates or suspended solids. A method to so alter the colloids so that they will be able to approach and adhere each other in the form of larger flux particles applies to the removal of colloid particles. Colloid destabilization. Colloids are stable because of their surface charge. In order to destabilize the particles, we must neutralize the charge. Such neutralization can take place by the addition of an ion opposite charge to the colloid. Since most colloids found in water are negatively charged, the addition of sodium ion, which is Na positive, should reduce the charge. Colloid stability. For colloids to remain stable, they must be really small. Most colloids are stable because they possess a negative charge that repels other colloidal particles before they collide with one another. Coagulants. Coagulants are the substance or chemicals that is added to water to accomplish coagulation. Its key properties are: first, trivalent cation; second, it should be non-toxic; and it third is insoluble in the neutral pH range. First key property is trivalent cation. The colloids most commonly found in natural waters are negatively charged. Hence, a cation is required to neutralize the charge. A trivalent cation is the most efficient cation. Second property is non-toxic. Obvious naman dapat nga non-toxic ang tubig. Third property is the insoluble in the natural pH range. The coagulant that is added must precipitate out of solution so that high concentrations of the ion are not left in the water. Such precipitation greatly assists the colloid removal process. Commonly used coagulants are aluminum and iron. Coagulant aids. Four basic types of coagulant aids. First, pH adjusters. Acids and alkalis are both used to adjust the pH of the water into the optimal range of coagulation. The acid most commonly used for lowering pH is sulfuric acid. Either lime or soda ash are used to raise the pH. Second basic type of coagulant aid is activated silica. When activated silica is added to water, it produces a stable solution that has a negative surface charge. The activated silica can unite with the positively charged aluminum or with iron flux, resulting in a larger, denser flux that settles faster and enhances enmeshment. The addition of activated silica is especially useful for treating highly colored, low turbidity waters because it adds weight to the flux. Third, clays can act much like activated silica, that they have a slight negative charge and can add weight to the flux. Clays are also most useful for colored low turbidity waters, but are rarely used. Polymers can have a negative charge, an ionic or positively charged cationic, positive and negative charge polyamphotype or no charge non-ionic. Polymers are long-chain carbon compounds of high molecular weight that have many active sites. The active sites adhere to flux, joining them together, producing a larger, tougher flux that settles better. This process is called interparticle bridging. The type of polymer, dose, and point of addition must be determined for each water, and requirements may change within a plant on a seasonal or even daily basis. Second part of water treatment is softening. Hardness is defined as the sum of all polyvalent cation. The common units of expression are mg per L as calco3 or milliequivalent per liter. Total hardness is often break down into two components. First, associated to HCO2 3, which is carbonate hardness, and second, associated with other anions called non-carbonate hardness. Non-carbonate hardness, or sometimes called permanent hardness, because it is not removed when the water is heated, it is much more expensive to remove than carbonate hardness. On the other hand, carbonate hardness or temporary or sometimes called as temporary hardness, which can be removed when the water is heated. When the water is heated. When the water is heated, the insoluble carbonates will precipitate and tend to form bottom deposits in water heaters. The formula for total hardness is carbonate hardness plus non-carbonate hardness. Lime soda softening. In lime soda softening, it is possible to calculate the chemical doses necessary to remove hardness. Hardness precipitate. The objective is to precipitate the calcium as CaCO3 and the magnesium as MgOH2. In order to precipitate CaCO3, the pH of the water must be raised to about 10.3. To precipitate the magnesium, the pH must raise to about 11. Softening reactions. The softening reactions are regulated by controlling the pH. First, any free acids are neutralized. Then pH is raised to precipitate the CaCO3. If necessary, the pH is raised further to remove MgOH2. Finally, if necessary, CO3 2 negative is added to precipitate the non-carbonate hardness. Split treatment. A portion of the raw water is passed by around the softening reaction tank and the settling tank. Several functions allows the water to be tailored to yield a product water that has 0.80 mEq per L or 40 mg per L as calco3 of magnesium. Allows for reduction in capital cost of tankage because the entire flow does not need to be treated. Minimizes operating costs for chemicals by treating only a fraction of the flow. Uses the natural alkalinity of the water to lower the pH of the product water and assist in stabilization. Ion exchange softening. Ion exchange softening can be defined as the reversible interchange of ions between a solid and a liquid phase in which there is no permanent change in the structure of the solid. In water softening by ion exchange, the water containing the hardness is passed through a column containing the ion exchange material. The hardness in the water exchanges with an ion from the ion exchange material. Third part of water treatment is mixing and flocculation. Mixing or rapid mixing is the process whereby the chemicals are quickly and uniformly dispersed in the water. Ideally, the chemicals would be instantaneously dispersed throughout the water. The precipitates formed during coagulation and softening should be brought in contact together to form even larger particles called flux. This containing process is called flocculation and is obtained by gentle mixing. The velocity gradient. It is the amount of shear taking place, or in a simpler term, it is the degree of mixing. The higher the velocity gradient, the more violent the mixing. A function of the power input into a unit volume of water. Na siya given formula which is velocity of gradient power is equal to the square root of the power input over the product of dynamic viscosity and the volume of water in mixing tank. Rapid mix. It is imperative that mixing be as instantaneous and complete as possible. Rapid mixing can be accomplished within a tank utilizing a vertical shaft, within a pipe using an inline blender, or in a pipe using a static mixer. Ang figure sa shaft mixer na makita diri, mao ni siya ang vertical shaft mixer, ang inline blender, o ang static mixer. Flocculation. Objective of flocculation is to bring the particles into contact so that they will collide, stick together, and grow to a size that will readily settle. Enough mixing must be provided to bring the flux into contact and to keep the flux from settling in the flocculation basin. Too much mixing will shear the flux particles so that the flux is small and finely dispersed. Therefore, the velocity gradient must be controlled within a relatively narrow range. The heavier the flux and the higher the suspended solids concentration, the more mixing is required to keep the flux in suspension. Upflow solid contact. Mixing, flocculation, and clarification may be conducted in a single tank. The effluent, raw water, and chemicals are mixed in the center cone-like structure. The solids flow down under the cone. As the water flow upward, the solids settle to form a sludge blanket. This design is called an upflow solid contact basin. Namin makita diri nga picture sa upflow solid contact basin. Fourth part of water treatment is the sedimentation. Overview. Particles that will settle within a reasonable period of time can be removed in a sedimentation basin, or called the clarifier. Sedimentation basins are usually rectangular or circular with either a radial or upward water flow patterns. Regardless of the type of basin, the design can be divided into 4 zones: inlet, settling, outlet, and the sludge storage. While our intent is to present the concepts of sedimentation and the design to design a sedimentation tank, a brief discussion of all 4 zones is helpful in understanding the sizing of the settling zone, the inlet zone, sludge zone, and the outlet zone. Inlet zone. To evenly distribute the flow and suspended particles across the section of the settling zone, the inlet zone consists of a series of inlet pipes and baffles placed about 1 meters into the tank and extended the full depth of the tank. Sludge zone. The configuration and depth of the sludge storage zone depends upon the method of cleaning, the frequency of cleaning, and the quantity of sludge estimated to be produced. Outlet zone is designed so as to remove the settled water from the basin without carrying away any of the flux particles. Sedimentation concepts. There are 2 important terms to understand in sedimentation zone design. The first is the particle flux, which is the settling velocity, and the second is the velocity at which the tank is designed to operate, or called the overflow rate. The settling velocity is greater than overflow. If the settling velocity is greater than the overflow rate, one would expect 100% particle removal. And if the settling velocity is less than the overflow rate, one would expect 0% particle removal. Settling velocity must equal the depth of the tank divided by the detention time. Determination of settling velocity. In design of sedimentation tank, one first determines the settling velocity of the particles to be removed and then sets the overflow rate at some values less than or equal to the settling velocity. Determination of particles settling velocity is different for different types of particles. Settling properties of particles are often categorized into one of these three classes. First class is the type 1 sedimentation. Type 1 sedimentation is characterized by particles that settle discretely at a constant settling velocity. They settle as individual particles and do not flocculate or stick to other particles during settling. Examples of these are particles are sand and grit material. Type 2 sedimentation is characterized by particles that flocculate during sedimentation. Because they flocculate, their size is constantly changing. Therefore, the settling velocity is changing. Generally, the settling velocity is increasing. Type 3 or zone sedimentation. In zone sedimentation, the particles are at a high concentration, greater than 1000 mg per L, such that the particles tend to settle as a mass and a distinct clear zone and sludge zone are present. Zone settling occurs in lime softening, activated sludge sedimentation, and sludge thickeners. Determination of overflow rate. There are different ways to determine effective particle settling velocities and consequently to determine overflow rates. First one is the discrete settling. In the case of type 1 sedimentation, the particle settling velocity can be calculated and the basin designed to remove a specific size particle. Sir Isaac Newton showed the particles falling in a quiescent fluid accelerate until the frictional resistance or drag of the particles is equal to the gravitational force of the particles. The three forces are defined as gravitational force, buoyancy force, and the drag force. The Reynolds number. The drag coefficient takes on different values depending on the flow regime surrounding the particles. The flow regime may be characterized qualitatively as laminar, turbulent, or transitional. Osborne-Reynolds developed a quantitative means of describing the different flows regimes using a dimensionless ratio that is called Reynolds number. For spheres moving through a liquid, this number is defined as r equal to the diameter of the sphere times the velocity of the sphere over the kinematic viscosity, or v which is equal to u over p, wherein ang u kay ang dynamic viscosity ug ang p kay ang density of the fluid. To understand more na ay picture nga nakabutang. Flocculant sedimentation. There is no adequate mathematical relationship that can be used to describe type 2 settling. Jar testing can also be used to determine the flocculated particle settling velocity and hence set the overflow rate. In a properly designed jar, this port is set at 10 cm below the water surface. After flocculation is complete, the mixer can be turned off and the floc allowed to settle. Part is the filtration. Water filtration is a process for separating suspended or colloidal impurities from water by passage through a porous medium, usually a bed of sand or other medium. Water fills the pores between the sand particles and the impurities are left behind, either clogged in the open spaces or attached to the sand itself. Methods of classifying filters. Classifying according to the type of medium used, such as sand, coal, dual media, or mixed media. Allowable loading rate is the loading rate. Loading rate is the flow rate of water applied per unit area of the filter. It is the velocity of the water approaching the face of the filter. Descriptions of filters based on loading rate. Number 1. Slow sand filters were first introduced in the 1800s. The water is applied to the sand at a loading rate of 2.9 to 7.6 m³ per day of m squared. As the suspended or colloidal materials is applied to the sand, The particles begin to collect in the top 75 millimeters and to clog the pore spaces. As the pores become clogged, water will no longer pass through the sand. At this point, the top layer of sand is scraped off, cleaned, and replaced. Slow sand filters require large areas of land and are operator intensive. Rapid sand filters. These filters have graded or layered sand within the bed. The sand grain size distribution is selected to optimize the passage of water while minimizing the passage of particulate matter. Rapid sand filters are cleaned in place by forcing water backwards to the sand. The operation is called backwashing. It is designed to operate at a loading rate of 120 m³ per day of m squared. Rapid sand filters are the most common type of filter used in water treatment today. Grain size characterization. The size distribution or variation of sample of granular material is determined by sieving the sample through a series of standard sieves or screens. The US standards sieve series is based on a sieve opening of 1 mm. Sieves in the fine series stand successively in the ratio of 1/4 to one another, of the largest opening in the series being 5.66 mm and the smallest 0.0337 mm. All material that passes through the smallest sieve opening in the series is caught in a pan that acts as the terminus of the series. Na-table diri nga nag-show o standard sieve series na which is sieve designation number, size of the opening, sieve designation number, and the size opening. Grain size analysis. The grain size analysis begins by placing the sieve screens in ascending order with the largest opening on top and the smallest opening on the bottom. A sand sample is placed on the top sieve and the stock is shaken for a prescribed amount of time. At the end of shaking period, the mass of material retained on each sieve is determined. Run of bank sand. Sand excavated from a natural deposit is called run of bank sand. Run of bank sand may be too coarse, too fine, or too non-uniform for use in filters. Within economical limits, proper sizing and uniformity are obtained by screening out coarse components and washing out fine components. In rapid sand filters, the removal of fines may be accomplished by stratifying the bed through backwashing and the scraping of the layer that includes the unwanted sand. Filter hydraulics. The head loss that occurs when clean water flows through a bed of clean filter media is an important design value to determine the overall head required to operate a filter. The flow through a clean filter of ordinary grain size at ordinary filtration velocities would be in the laminar range of flow depicted in Blake-Kozeny equation, that is dimensionally homogeneous. The fifth part of the water treatment is the disinfection. Used in water treatment to reduce pathogens or disease-producing microorganisms to an acceptable level. Disinfection is not the same as sterilization. Dili siya para sa sterilization because ang sterilization implies the destruction of all living organisms in the water, while in disinfection, dili siya kailangan nga sterile, dili mo siya kailangan patyon tanan living organisms sa water kay naapoy uban nga which can be helpful. Three categories of human enteric pathogens are normally of consequence of bacteria, viruses, and amoebic cysts. Purposeful disinfection must be capable of destroying all three. To be of practical service, water disinfectants must possess the following properties. They must destroy all the kinds of number of pathogens that may introduce into water within a practicable period of time over an expanded range in water temperature. They must meet possible fluctuations in composition, concentrations, and conditions of the water or wastewaters to be treated. They must be neither toxic to humans and domestic animals nor unpalatable or otherwise objectionable in required concentrations. They must be dispensable at reasonable cost and safe and easy to store, transport, handle, and apply. Their strength or concentration in the treated water must be determined easily, quickly, and automatically. They must persist within disinfected water in sufficient concentration to provide reasonable residual protection against its possible recontamination before use, or because this is not normally attainable property. The disappearance of residuals must be a warning that recontamination may have taken place. Disinfection kinetics. Under ideal conditions, when an exposed microorganism contains a single site vulnerable to a single unit of disinfectant, the rate of die-off follows Chick's law, which states that the number of organisms destroyed in a unit time is proportional to the number of organisms remaining. Chlorine disinfecting actions. Chlorine disinfection involves a very complex series of events and is influenced by the kind of extent of reaction with chlorine reaction material, including nitrogen, temperature, pH, and the viability of test organisms and numerous other factors. Such factors greatly complicate attempts to determine the precise mode of action of chlorine on bacteria and other microorganisms. Microorganisms killed by disinfectants is assumed to follow the CT concept, that is, the product of disinfectant concentration and time. Time yields a constant. CT is widely used in the surface water temperature rule as a criteria for cyst and virus disinfection. Chlorine or ammonia reactions. Reactions of chlorine with ammonia are of great significance in water chlorination processes. When chlorine is added to water that contains natural or added ammonia, the ammonia reacts with HOCl to form various chloramines which, like HOCl, retains the oxidizing power of the chlorine. The reaction between chlorine and ammonia may be represented as follows. Nahal siya kita nga reactions diri. First one is ang monochloramine, ang ikaduha ang dochloramine, o ang ikatulo ang trichloramine. Practices of water chlorination. Evolution. Early water chlorination were applied for the purpose of disinfection. Chlorine ammonia treatment was soon thereafter introduced to limit the development of objectionable taste and odor, often associated with marginal chlorine disinfection. Subsequently, superchlorination was developed for the additional purpose of destroying objectionable taste and odor producing substances, often associated with chlorine-containing organic materials. The introduction of water breakpoint chlorination and the recognition that chlorine residuals can exist in two distinct forms established contemporary water chlorination as one of the two types, combined residual chlorination or free residual chlorination. Combined residual chlorination involves the application of chlorine to water in order to produce, with natural or added ammonia, a combined available chlorine residual and to maintain that residual through part or all of a water treatment plant or distribution system. Combined available chlorine forms have lower oxidation potentials than free available chlorine forms and therefore are less effective as oxidants. Moreover, they are also less effective disinfectants. When a combined available chlorine residual is desired, the characteristics of the water will determine how it can be accomplished. First, if the water contains sufficient ammonia to produce with added chlorine a combined available chlorine residual of the desired magnitude, the application of chlorine alone suffices. Second, if the water contains too little or no ammonia, the addition of both chlorine and of ammonia is required. Third, if the water is or has an existing free available chlorine residual, the addition of ammonia will convert residual to combined available residual chlorine. A combined available chlorine residual should contain little or no free available chlorine. The free residual chlorination involves the application of chlorine to water to produce either directly or through the destruction of ammonia a free available chlorine residual and to maintain the residual through part or all of a water treatment plant or distribution system. Free available chlorine forms have higher oxidation potentials than combined available chlorine forms and therefore are more effective as oxidants. Moreover, as already noted, they are also the most effective disinfectants. When free available chlorine residual is desired, the characteristics of the water will determine how it can be accomplished. First, if the water contains no ammonia or other nitrogenous materials, the application of chlorine will yield a free residual. Second, if the water does contain ammonia that results in the formation of combined available chlorine residual, it must be destroyed by applying an excess of chlorine. Chlorine dioxide or ClO2, very strong oxidant formed on site by combining chlorine and sodium chloride, often used as a primary disinfectant in inactivating the bacteria and cyst, followed by the use of chloramine as a distribution system disinfectant. Does not maintain a residual long enough to be useful as a distribution system disinfectant. Also been associated with taste and odors in some communities. The health concerns, taste and odors, and relatively high costs have tended to limit the use of chloride dioxide. Ozonation. Ozone is pungent smelling unstable gas. It is a form of oxygen in which three atoms of oxygen are combined to form the molecule O3. Because of its instability, it is generated at the point of use. The ozone generating apparatus commonly is discharge electrode. To reduce corrosion of the generating apparatus, air is passed through a drying process and then into the ozone generator. Ultraviolet radiation disinfect waters by rendering pathogenic organisms incapable of reproducing. This is accomplished by disrupting the genetic material in cells. The genetic material in cells, namely DNA, will absorb light in the ultraviolet range, primarily between 200 nm and 300 nm wavelengths. The inactivation of microorganisms by UV is directly related to UV dose. Naay factors na nag-affect sa UV disinfection system. First, ang particles. Second, ang turbidity. O ang third, ang suspended solids. It can shield pathogens from UV light or scatter UV lights to prevent it from reaching the target microorganisms, thus reducing its effectiveness as disinfectant. Now, fourth factor, ang organic and inorganic compounds, such as iron and permanganate, can reduce UV transmittance by absorbing UV energy, requiring higher levels of UV to achieve the same dose. It is recommended that UV systems be installed downstream of the filter so that removal of particles and organic compounds is maximized upstream of UV. Advanced oxidation processes or AOPs. AOPs are combinations of disinfectants designed to produce hydroxyl radicals. Hydroxyl radicals are highly reactive, non-selective oxidants able to decompose many organic compounds. Most noteworthy of AOP processes is ozone plus hydrogen peroxide. The sixth part of water treatment is the adsorption. Adsorption is a mass transfer process wherein a substance is transferred from the liquid phase to the surface of a solid where it is bound by chemical or physical forces. In water treatment, the adsorption the adsorbent is activated carbon, either granular or powdered. PAC is fed to the raw water in a slurry and is generally used to remove taste and odor causing substances or to provide some removal of synthetic organic chemicals or the SOx. JAC, on the other hand, is added to the existing filter system by replacing the anthracite with JAC, or an additional contactor is built and is placed in the flow scheme after primary filtration. The design of the GAC contactor is very similar to a filter box, although deeper. Granular activated carbon, or the GAC. Used as an alternative for taste and odor control, many plants have replaced the anthracite in the filters with GAC. It will last from 1 to 3 years and then must be replaced. It is very effective in removing many taste and other compounds. Used for synthetic organic compounds removal either as a filter media replacement or as a separate contactor. GAC has been used to remove naturally occurring organic matter that would in turn reduce the formation of DBPs. Powdered activated carbon, or the PAC, is fed to the raw water in a slurry and is generally used to remove taste and odor causing substances or to provide some removal of synthetic organic chemicals. Biologically derived earthly musty odors in water supplies are a widespread problem. Their occurrence interval and concentration vary greatly from season to season and is often unpredictable. As mentioned, one of the most popular methods for removing these compounds is the addition of PAC to the raw water. The dose is generally less than 10 mg per L. The last part of the water treatment is the membranes. A membrane is a thin layer of material that is capable of separating materials as a function of their physical and chemical properties when, when a driving force is applied across the membrane. In the case of water treatment, the driving force is supplied by using a high pressure pump and the membrane type is selected based on the constituent to be removed. Na may makita diri nga figure nag-show sa schematic representation of contaminants separated by a membrane. Nakita nimo sa feed nga portion dagan pa kayo og mga contaminants nga after mo pass through sa membrane mo gamay na siya permeate. Membranes can be described by a variety of criteria including membrane pore size, molecular weight cutoff, membrane material and geometry, targeted materials to be removed, type of water quality to be treated, and or treated water quality. Pressure-driven membrane processes. Reverse osmosis. This process has traditionally been employed for the removal of salts from brackish water and seawater. It depends upon applying high pressure across the membrane in order to overcome the osmotic pressure differential between the saline feed and product waters. Nanofilters. This process, also called membrane softening, lies between reverse osmosis and ultrafiltration. This membrane process employs 500 to 1000 kilopascal for operation, while it provides removal of ions contributing to hardness. The technology is also very effective for removal of color and DBP precursors. Ultrafiltration. Ultrafiltration membranes cover a wide range of MWCOs and pore sizes. Operational pressure range from 70 to 700 kilopascal depending on the application. Tight ultrafiltration membranes may be employed for removal of some organic materials from fresh water, while the objective of loose membranes is primarily for liquid separation, example, particle and microbial removal. Microfiltration. A major difference between microfiltration and loose ultrafiltration is membrane pore size. The pores of microfiltration are approximately an order of magnitude greater than those of ultrafiltration. The primary application for this membrane process is particulate and microbial removal. That's all for the chemistry of water treatment. Thank you.